Okay, can you all hear me? Right. Maybe by trying to explain the title of my talk, what I'll do is give you an overview of what I'm going to discuss in the first slide here. What I want to do is talk about composite laminate in the context of generalized continua, that is, materials that exhibit a distinct size effect when they're loaded. I also want to then talk about the size effect paradox in composite laminates. We'll show that the size effect depends on the order in which you lay up the laminate. And then in the second part of the talk, I'll get on to discuss some fracture mechanics. So what are the implications of these size effects for evaluating energy release rates of delamination? And then I'll finish with some conclusions and actually a question as well. Okay, so what I'm looking at is a simple two-constituent laminate consisting of alternate layers, and these are materials A and B that have moduli EA and EB respectively, and obviously EA differs from EB. In this laminate, the surface layers are always comprised of material B. As I've said, that has modulus EB. The laminate is going to be loaded in bending, and what I'm going to do is try and determine how the flexural rigidity and stiffness change as the number of layers in the laminate changes, but I maintain the thickness of the individual layers. There's actually two cases I need to consider. On the left there, you've got the case where material A forms the core layer, and on the right there, material B forms the core layer. And I've said that in this analysis there are n plies of material A, and therefore n-1 internal plies of material B. And then I've got the two surface layers of material B, so that gives me 2n plus 1 layers in the laminate in total. And the other subtlety in this is you'll notice in both figures there that the surface layers, the thickness of the surface layers is half the thickness of the internal layers of material B. The reason for that is so that as I vary the thickness of the laminate and keep adding more plies, the volume fraction of each material remains constant. So I'm going to determine the flexural rigidity of these laminates and find out how that flexural rigidity varies as I change the number of plies. And to do that is quite straightforward. To get the flexural rigidity of the laminate, all I have to do is sum up the flexural rigidity of each ply within it. And I've got two cases here. This is the case where n is odd, the figure I had on the left, and I've got the case where n is even here. The first term in each summation is the flexural rigidity of the core layer. I've then got these two summation terms, which are the intermediate layers, and then I've finally got the surface layer in the fourth term in each expression. And in both cases, it's interesting that the result for the flexural rigidity comes out to be this expression here. And this expression for the flexural rigidity, well, you can see that the first term here involves n cubed. Remember, n is the number of layers of one of the materials. So this term is going to vary something like depth cubed, but we've now got this additional term here. In the paper, I actually plot out this variation in the flexural rigidity as a function of the number of layers, but it's not immediately obvious to observe the size effect. So an alternative way of thinking about it is shown in the next slide here, where instead of determining flexural rigidity, I determine the stiffness. Here I've just determined the stiffness in 3-point bending because of its experimental simplicity, but I do the same exercise for 4-point bending or whichever mode of loading was my favourite. So here I've calculated the stiffness now, and basically I've got to multiply through by 48, divide through by the length cubed, I think. But what I'm doing now is that I'm fixing the aspect ratio of all the laminates. So I'm in a situation in which I've got laminates of different thickness, but I'm scaling the size of them so that the length to depth ratio always remains constant. And I'm making various other assumptions like they're slender laminates. So this parameter A here is now constant. And if we know the laminate depth must be the sum of the individual laminate thicknesses, and if you like, the mean modulus of the section, or the modulus I would get if I were doing a simple uniaxial test is given by this expression, then the expression at the top here simplifies down to this thing here. So this expression of stiffness now involves a leading term here, which involves the length to depth aspect ratio A, but remember that's constant for all sample sizes, and then I've got this term here, which is the size effect term. And I'd also draw your attention to this negative sign here, because depending on the relative size of the moduli here, this size effect can change sign. So let's have a look at what happens now if I determine stiffness as a function of the laminate depth. And in the case where the modulus of the surface layers is greater than the other material, so EB is greater than EA, I get this size effect here. Be careful, because this measure on the horizontal axis is a reciprocal measure of the sample depth. So the small sample is out here on the right, and the large samples are over here on the left. So as the samples are getting smaller in this case, they're becoming relatively stiffer. And this size effect agrees what we would expect of a Kossarek type material rather than a Cauchy type material. And a Kossarek material, in Kossarek elasticity theory, size effects are accounted for. You'll actually see this simplified expression here. You've got the leading term here, which is the stiffness of a homogeneous beam, and then you've got this correction term that involves this characteristic length parameter LC. If I assume that the modulus of material A is now greater than material B, so the compliant surfaces, the size effect does the opposite thing. So as I go to the smaller samples, the material laminate is becoming more compliant. And these, what we call paradoxical size effects, have been observed previously in experimental work on cortical bone, and it was trying to explain that work that motivated us to come up with this laminate model. Also by others on 2D virtual foams, and by ourselves on some, again, idealized representative materials. Okay, now on to, we can also, of course, look at how the size effect varies as I change the volume fraction of the compliant material. So when I've got mainly compliant material, I've got the material behaves in an almost homogeneous way. As I increase the volume fraction, here I've got mainly the stiff material. If I then increase the volume fraction of the compliant material, the size effect goes up, and then I reach a maximum, and then as I move to mainly compliant material in the laminate, compliant material is dominating, and the material starts to become homogeneous again. And it's interesting to know that the two size effects that I get when I've got stiff layers and compliant layers, they kind of reflect one another, but they're not exactly opposite if you look at the numbers in detail, the values in detail. Okay, now on to some fracture mechanics. So this is the kind of generic laminate sample that we're all used to, and what I've done now is I've taken my heterogeneous laminate and I've put delamination into one of the compliant layers there. According to Gordon Williams' analysis, going back to 1988, the energy release rates for this material are given by these two expressions here. And you get this by, of course, partitioning the total energy release rate, and it assumes that the loading associated with mode 1 and mode 2 can be written in terms of the applied moments, given these two expressions. I think in the literature there's general consensus that this is correct for symmetric samples, but I think it's more contentious for the asymmetric sample. So what I'm going to do, of course, is I'm going to take the result I've got now for the heterogeneous laminate, the result for the flexural rigidity that I had earlier on, and I'm going to substitute that result in here. So rather than assuming homogeneity, I'm now using this heterogeneous laminate model that exhibits this size effect. Before I do that, let's just take the homogeneous case a little bit further. So I think in your paper, Gordon, you actually assume homogeneity and you're able to simplify those expressions and get these results for G1 and G2. And the thing to note is that in the homogeneous case, G1 and G2 will be independent of depth if you scale loads according to this relationship there. So providing the applied moments are scaled, the square of the applied moment scales according to depth cubed, then G1 and G2 will be sample size independent. So let's look at what happens now in the heterogeneous case where, as I say, I use the size-dependent flexural rigidity, and this is now the case of a symmetric sample. So I've assumed that the depth of the lower arm is the same as the depth of the upper arm. I've tried to use some realistic properties here. So EA is 100 times EB, so you can think of EA as being some reinforcing fiber plies. EB might be some resin interface layer. And I've also assumed that the thickness of the reinforcing plies is 10 times that of the interface layers. I've set here M1 equal to 0, so one of the applied moments is 0, and that gives me a nominal mode mixity. Sorry, I've defined mode mixity as just the ratio of G2 to G1. In the homogeneous case, the mode mixity would be 0.75. So this is a symmetric sample, but mixed mode loading. And you can see what happens in these figures. On the left here, we've got two energy release rates, G1 and G2. And when I've got lots of plies, you can see that everything, sorry, I've also normalized these with respect to the homogeneous case. So when I've got lots of plies, everything's hunky-dory, and the solution goes off asymptotically to 1 there, so the heterogeneous case converges with the homogeneous case. But when I come back here, and I've got few plies in the laminate, you can see that G1 and G2 diverge from the homogeneous value. And not only that, G2 diverges more than G1, so of course I get divergence in the mode mixity as well when I define it in this way here. Divergence in the energy release rates is quite significant for these particular choices of parameter values. The divergence in the mode mixity is less. The second case I've looked at, which is not actually covered in the paper, is the asymmetric sample now. So I'm using the global partitioning, which may be controversial, of course, but now I've got one arm is one of the delaminating arms is 4 times thicker than the other. I've kept the same ratio of moduli, the same ratio of thicknesses there, and now I've set one of the applied moments equal to 9 times the other one, so I've still got the same nominal mode mixity as I had for the symmetric sample. Again, when I've got lots of plies in there, everything is fine, and the solution converges to the homogeneous case. As I come back here though, and I've got few plies, you can see G1 and G2 diverge, but in this asymmetric case, G1 now diverges more than G2, and as a consequence, the mode mixity converges from below rather than from above. So there's some dependence upon the energy release rates, but mode mixity on the sample geometry as well. Okay, finally some conclusions. What I've first of all shown is that a laminate material may exhibit a greater variety of size effects than forecast by generalized elasticity theories such as Coser elasticity. In a laminate, I've said the energy release rate and their mixity may be influenced by, hopefully shown that they're influenced by the sample size. So when you have a very thin laminate with just a few plies in it, your energy release rates, your nominal energy release rate may be different from the case where you have a thick ply. It also depends on sample geometry, as I've shown by looking at both the symmetric and asymmetric cases. I've not shown it here, but in the paper I show some results to show that the ratio of interface layer thickness to reinforcing ply thickness also influences in the energy release rates and their mixity. And I finished off, as I promised, with a question: what are the implications of all this for developing standard protocols for doing delamination tests? Okay, thank you.
Thank you very much for your